Greetings, and thank you for joining us for another SANS ICS concept overview. I'm Don C. Weber of Cutaway Security and a certified SANS instructor. In this ICS concept overview, I'm joined by Jaime Lightfoot, an electrical engineer and member of the Grimm cybersecurity and research team. Jaime's here to introduce us to the CANbus protocol. She will discuss how CANbus is implemented in vehicles and other sectors where communications are subject to a variety of electrical interferences. If you enjoy this video and topics we cover in the SANS ICS concept overviews, be sure to like and subscribe to this channel. Leave a comment if you have a question about this topic or suggestions for future content. All right, the next SANS ICS concept video, for this one, we're going to talk about CANbus and what it is actually made up of. And so joining us to do that is Jaime Lightfoot from Grimm. So Jaime, thank you for joining us. And can you tell us just a little bit about yourself and then start talking about CANbus? Let us know about that.
Sure. Well, thanks for having me, Don. My background is a bit varied. I went to school for electrical engineering, so I've kind of seen the engineering side of automotive. I worked as a software developer for a little bit, and now I work at Grimm on the sci-fi team, which stands for cyber physical. We do a lot of car hacking, ICS, just a lot of cool taking things apart, breaking them, and that has exposed me to quite a bit of automotive security.
Excellent. Well, I appreciate you coming on board. And actually, this is a response to I've got a question and a request to talk about CANbus, specifically about robotics. But I knew you had a vast experience around implementing the CANbus within vehicles. So, can you help us understand that a little bit?
Sure. So yeah, like you said, a lot of my experience is in the automotive space. So the examples that I'm going to talk about today are in automotive, but you might run into this in ICS, in robotics, like you said, maybe even aviation. So at a high level, let's talk about what CAN is and why we might want to use it. It stands for Controller Area Network. It's a communication protocol that's really well suited to electrically harsh environments like you might see in automotive and industrial. It was invented by Bosch in the 1980s as a way of providing like a more reliable alternative to the point-to-point wiring that they used to do in cars. And now, because of an EPA law, CAN is in all cars, at least within the US, and it also is in a bunch of other applications. So at a very, very high level, it's a communication protocol that allows all of the electronic control units, which are also called nodes. So think of like an engine controller, brakes controller, all of the little computers in a car, microcontrollers that are telling mechanical parts what to do and reporting information to other parts. It allows all of those units to communicate on a shared network. So cars are way more complex now than they were in the 80s. We've got, Wi-Fi, touchscreens, all sorts of sensors, but CAN still solves a lot of the problems that motivated the invention of CAN back in the 80s. And the biggest thing that it offers is reliability. And that's because vehicles are really electrically noisy environments. You've got all sorts of moving parts that are, inducing interference and noise onto electrical lines. Things are really exposed to really hot or cold temperatures. And you also have a surprisingly large amount of wire in the wire harness. I want to show you a photo from, I guess, a year and a half ago. It was pre-COVID. So this is a photo of the entire wire harness from a Ford Escape taken out of the car with a lot of effort and work and sawing things apart and laid out on our lab floor. You can see this is kind of the bumper. We've got tail lights. We have some sensors back here. There's a backup camera. There's, what else can I point out? You can see the roof antenna here. There's audio, there's telematics box, think of like OnStar kind of thing. Here's some door harness that is detached. There's a bunch of connectors to help install it a little bit easier. And then all of this up here is what is under the dashboard and then what's under the hood.
So is this now Grimm is Grimm travels around with a display demo called CP30, CP30?
We just call it 3PO.
Yeah, 3PO, excuse me. And 3PO, yes. And so is this from that, or was this after that?
This is after that. So 3PO is like a miniaturized version of this. This is probably like 30 feet from one end to the other. 3PO is this kind of folding display that we can pack into a suitcase and bring to conferences, but it's the same idea. We took a car, we kind of scavenged parts out of it. So the engine controller, the transmission controller, the touch screen, some dash displays, and then we set that up so that people can plug into it and interact with it and kind of make the car think that another genuine device from the car is talking.
So was this that we're looking at right here, was this all pulled out of an existing vehicle, or were the parts purchased and assembled afterwards?
This was taken from a Ford Escape that got, I want to say, T-boned in the side. So the car was totally wrecked. The frame was just smashed pieces on the side. But all of the electronics that we were interested in were completely intact. So we hauled the car in, took it apart. You would not believe how many methods of fastening harnesses there are. You've got tape, screws, zip ties, everything. So it's a huge effort to get all of this out. We'll take all of it out. We know that it worked because before we take it out, we can kind of interact with it while it's still in the form of a car. And then we turn it into a test bench that like universities or schools or other training centers use to teach people about automotive security.
Were there and this question just kind of popped in my mind when we were talking about this. You know, I think about vendors integrate, working on this, whether it's adding a stereo system or changing out a window or something like that. Was this all Ford stuff, or could you see other people that had integrated into the wiring harness, adding different components and so forth?
I think this was all from Ford, but the way that the automotive industry works, you have an OEM like Ford, and then they'll plan out the whole car, but then they kind of farm out the different pieces to tier 1, 2, and 3 suppliers. What that means is that if they farm out the design of, say, the brake controller to a different company, that company might also make brake controllers for a different OEM. So even though it is designed to operate in a Ford vehicle, you might see similarities between a type of component in a Ford car versus a GM car versus Chrysler or whatever. So yeah, you do see some similarities between different vehicles, but this one I think was all original. Maybe the audio system was different.
Yeah, I didn't mean to get you off track, so.
No, it's fine. Good question. So this harness looks like a ton of wiring, and it is. There are a couple antennas in here. There's some ground wires, but the main thing that's going on in here, at least that we're interested in, is the CAN high and CAN low differential pair. So the way that CAN works is that you have two wires that are known as a differential pair. You've got CAN high, which is the blue line in this diagram, and then CAN low, which is the red line. When these two wires are at the same voltage, in this case 2.5 volts, it's known as a recessive bit. which is a logic 1, which is kind of different than what you think. And then when the lines are asserted and you have a voltage differential between the two, in this case you have 2-volt differential between the dominant and, or sorry, not the dominant, the CAN high and CAN low pair making a dominant bit, it is a logic 0. CAN nodes need to have a common ground. You need termination at each end of the bus, usually 120 ohms, so that this state can exist. And except for CAN FD, all the nodes need to be configured to run at the same speed, which is either going to be for low speed CAN 125 kilobits per second, or 1 megabit per second for high speed CAN. So earlier I talked about how cars are electrically noisy environments. So if we're looking at this diagram and think, what would happen if there was some kind of big spike on the line or noise on the line from something? Because you've got this differential pair, if we've got a big spike here and we have the same big spike here because these are twisted together, it's going to come out in the wash because the devices listening on the CANbus are looking at the difference between the two and not the absolute voltages. So if you have a big spike on one, you're going to have a big spike on the other. You're just looking at the difference and it's going to come out in the wash, which means that you've got a way to withstand that noise. You don't have to rely on the car being an electrically nice environment for the ECUs.
Okay, so it's kind of like an error checking, I guess. In a way, it's not a CRC, cyclical redundancy check, but it's just another way of telling the difference between or reducing the amount of errors for those transmissions in that noisy environment.
Mm-hmm.
Okay.
Which is important for cars and robotics and industrial equipment because the price of being wrong is pretty high.
Interesting.
So for each of the components that you put on the CANbus, so we talked about how you've got the audio here, telematics, you've got the different lights, the antennas. The more interesting stuff is, of course, farther away in the photo. But you want each of the devices to be able to plug in onto this harness and just be plug and play and be able to communicate with the other devices. So you need each device needs to have a CAN transceiver that can send messages out on the CAN high and CAN low lines. You need to be on the same speed. And in software, you have to have the same kind of concepts of what messages are being sent. I've got a photo of this from a more conceptual standpoint that I think might be useful.
Oh, okay.
So the photo that I just showed doesn't really give you an idea of where the components are in the car, other than the very front and the very back.
Okay.
Here you can see you've got cruise control, you've got brake system, you've got the accelerator, you've got door control. That all need to talk to each other, or at least be aware of what's happening in the car. So if OEMs can add whatever devices they want on here, as assuming that it conforms to the top level design that they had for the car, how do the different devices know which ECUs are sending out messages and then which ones they should listen to? If we talk about let's talk about the second part first. So each device is programmed to know what messages it's interested in. For example, the engine knows that it needs to listen to the transmission, it needs to listen to maybe some heat sensors, things like that. So while it might be electrically receiving all of the messages on the bus, there's some kind of filtering going on where the microcontroller decides what it's actually interested in acting on. There's also an important concept in the CAN protocol that helps decide which devices get priority, which is called arbitration. We obviously want the more important devices. As another, coming back to the simplified example, we want the engine and transmission and brakes to have more priority over things that are less important. For example, the radio or moving the window up and down. So this priority is mapped to arbitration IDs. And these IDs help identify which CAN messages are being sent. I'm trying to be nuanced here and not say that the arbitration IDs map to devices, because that's not quite it. Instead of thinking one arbitration ID per device or per ECU, think one arbitration ID per type of message from an ECU. So ECUs can send out these CAN messages with different arbitration IDs. Maybe the engine has an arbitration ID that it sends out like a category that it sends out the most important messages that need to be acted on right away. It might also have more informational, less urgent messages, and it would send that out over a different arbitration ID. So the devices are all listening on their shared bus. There might be segmentation. We'll talk about that later. And if the bus isn't busy, if there's no one currently talking on the bus, then a device can start a message. So if everyone is waiting to talk on the bus, what happens if two devices want to talk and start talking at the exact same time? Arbitration is going to help us sort this out too, and this is also kind of where where this dominant recessive being opposite of what we expected comes in. So we'll get a photo of a CAN frame in just a second, but towards the start of the CAN frame, you send out your arbitration ID. So in this example, we've got two devices, device A and device B. We'll say that device A has we'll say that device A has an arbitration ID of 7FA and device B has an arbitration ID of 7FF. So as they're sending this out, CAN devices have a way of synchronizing. As they're sending this out, the other devices can't actually tell that there are two different messages being sent out because they're identical at the beginning. So they send out a 111 for the first byte, which is 7. They send out 4 ones for F. And then when we get to the last byte, there's a conflict. So they both send out a 1. And then when device A sends out a 0, it is forcing the line, it is asserting the line and creating a dominant bit to send that 0, whereas device B wants the two lines to stay the same. So device A is a lower number. It's got a 0 earlier on in the arbitration ID, and it is going to electrically create a state where device B cannot announce its arbitration ID, and that device will realize that and then drop off, stop transmitting, drop off the line, and wait until the line is quiet again. So that's kind of a clever way to electrically arbitrate who can talk at a given time.
Now, these will they be transmitting at exactly the same time? I mean, I know for Ethernet we have collision detection, and there's some timing around that. Would both of these be starting at the same time, or do they wait for a specific period before transmission?
Don't actually know that off the top of my head. I know they're going to wait. There's an end of frame that they're going to listen for.
Okay.
I'm not sure.
Yeah, not a problem. Just kind of I'm curious about this, but I guess the biggest thing that for this that you're trying to get across is prioritization of messages. What has priority to transmit and to be passed from device to device, I guess, so to speak.
Yeah. So not each device, but each arbitration ID is ranked in priority based on how low the number is. So if you have something that is like super important from the engine, the OEM is going to assign that a lower priority number, or a lower arbitration ID, which is a higher priority, which means that it's going to be the top case in any kind of conflict, and it will win out and be able to transmit ahead of less important devices.
Okay.
And that's all like electrically and enforced with the electrical design of the protocol, but also in the software.
So is this a part of the whole packet that's being sent, or is this a starting packet and then there'll be follow-on data after that?
This is the start of the packet. Let me actually pull up what a CAN frame look like.
Well, hopefully I didn't jump you ahead.
Oh no, you're good.
Okay.
So we got a high level idea of what arbitration IDs are. We know that they help decide priority. We know that the electrical design of the protocol is kind of enforcing the, wait your turn and let the most important message come through first. If we look at what a CAN frame looks like, this is the part that we just talked about, the ID here in front.
Okay.
So we actually have a startup frame, and then we have the ID. The next bit here is RTR, or remote transmission request. So usually the devices are just broadcasting something about their own state, and then other devices that are listening can act on it or not. But the CAN protocol also makes it so that you can request data from another source. And the way that you do that is by setting the RTR bit to 1. So there's 4 types of CAN frames. There's the remote CAN frames, which we just talked about, which is, hey, I need some message from you, other device. Could you send that back? There's data frames, which is the most common, which is like, here's what's going on with me. If you want to act on this, that's fine. There's error frames, which are sent out by nodes that think they've detected some kind of error condition. And then there are overload frames, which are mostly used to inject a delay between other types of frames. So after the RTR is the control section. You have a bit in there that specifies whether you have an 11-bit ID, as in this case, or you can have an extended 29-bit ID. If the IDE bit is set, then you're going to have some more data in here that will. You're going to have another 18 bits that will be combined to have a 29-bit identifier. In this case, we just have the original 11-bit identifier. Okay, so after that, you've got up to 8 bytes of data, which does not sound like a lot of room, and you'd be correct. We'll get into that a little bit more later. There is a CRC, so you've got some more error checking on top of the kind of electrical reliability that was already built in that we talked about earlier. Again, we want this because if the devices that are receiving this get bad information and they act on it and they don't have any kind of way to detect that it was bad information, then there might be bad consequences. There's an ACK bit, so the other nodes that are going to receive it, if they don't find any kind of error, they're going to transmit a dominant level, so the voltage differential. They're going to start the lines so that we get a zero logic bit sent out. If the transmitter, so if I'm sending the message and I don't detect the low, right, I don't detect a logic 0 on the line at that point, then I know that either no one heard my message or they heard it and they thought that something was wrong with it. So that's another way to kind of build in some kind of reliability into the system. And then lastly, you've got the end of frame, which is just going to be 7 bits that are all recessive. After that point, the line is quiet and we can start another frame. So I said we talk about the data and what exactly is being sent here. If you were to open up CAN traffic in a program like Wireshark or one of the tools that we'll talk about later, you're just going to see a mess of what looks like random values just scrolling by. So trying to interpret what these numbers mean is very application specific. The values are going to mean something different for different OEMs or different like industrial systems or whatever. And there are 2 ways that you might find out what these mean. So the CAN protocol lets engineering companies or whoever is manufacturing these parts kind of encode their own meanings into different messages. So it might be that this is a temperature or a voltage level. It could also be something where you have to look bit by bit and say, okay, if this bit is 1, that means that, I don't know, your brights are on or something like that. All of that is application specific, and you've got 2 ways of figuring it out. You can either get the official files, DBC files that are going to translate between these numbers and the actual meanings for each of the messages, or you can reverse engineer it yourself, which is going to take quite a bit longer. But it might be your only option because some companies aren't really open about this stuff.
So the CANbus standard is more of a way of passing information. The format of the data is specific to vendors, possibly following some formatting standards, but really whatever their engineers designed it for. Is that kind of the breakdown?
Yeah, it's not, it's not a total free-for-all, but it is set up in a way that the OEMs can implement it how they'd like to in their company. I also thought just now there are a lot of car hobbyists. So if you're watching this video and you're interested in automotive cybersecurity, you might find this kind of information on hobbyist forums, because there are people who reverse engineer cars for security reasons, but there are also people who reverse engineer cars just because they love modding their cars or rally racing, things like that.
Right, and they're doing things like doing something over and over again, like open the door, close the door, capturing all of that, open the door, close the door, and seeing what changed or seeing what types of messages are produced from that, and then kind of narrowing the field associated with that to understand what's being passed. Is that kind of your day-to-day when you're working with this stuff?
Mm-hmm. We actually, so with 3PO that you mentioned earlier, one of the kind of 1-page lab walkthroughs that we do at conferences is there's one where we send out a brake fluid level message where we already know what the value is, and we give that value, the 8-byte value, to the people who are trying to do the lab. But there's another one where we've got the keys. We hit the unlock button as we're capturing traffic. So start recording, unlock, stop recording, and then we kind of inch that in from both sides and keep replaying it when we replay it, it will unlock the door because the devices are just responding to the messages that they're receiving. They're not doing any kind of authentication. Excuse me. And then we can kind of scooch our way in until we get to the one message that is the unlock the car message. And you can probably imagine that can be useful for cybersecurity, but it's also, just a good, easy way of narrowing in on something that you're trying to figure out when you don't have a whole bunch of insider information.
And that's actually, I think that was one of the recommendations, kind of like the hello world for CANbus when dealing with cars. Interact, plug in, see if you can see it, then see if you can detect how the messages associated with unlocking the door, and then unlock the door yourself. So that's kind of like the hello world. I thought that was pretty interesting. I haven't been able to do it just yet, but definitely understand that.
Maybe after COVID.
I need to rent a car. I didn't say that out loud.
Or that. So we talked a little bit about cybersecurity. Let's talk more about how not really secure this is. This was made in the 80s, and the people making this weren't thinking like, is this safe for a connected car? Because that wasn't a thing back then. So this protocol that was optimized for reliability and optimized for the world at that time now has a bunch of security concerns because we keep adding wireless access and telematics and everything to cars, and just opening up the attack surface. So you might have noticed earlier in some of the examples that there was no mention of authentication. So if I can figure out through reverse engineering or looking online, or maybe I've got the DBC files, if I can figure out what an arbitration ID is for a given type of device message, I can construct a CAN frame and send that out on the bus. I can use something like this device here, which we'll talk about in just a minute. I can send out that message and essentially pretend to be, I can pretend to be the brakes. I can pretend to be the body controller in the example of unlocking the car door. I can, pretend to be whatever part I want, and the other devices are going to respond as though I were actually that part on the CANbus.
So it's another of what a lot of information security professionals that aren't familiar with control networks, they hear about these protocols that are insecure, that are sending information. They're not protected by some type of tunnel or encryption layer, and so this is an example of that. But it's also an example of something that probably would, by encrypting these messages, would induce some type of delay in processing on the both transmission. Is going to make the messages bigger, but also the processing on the endpoints is going to be more complex as well. So this is a good example of that. Would implementing encryption on these message exchange, would it have a serious impact on the function of these endpoints and devices?
I haven't run the numbers, but I would like to say yes. These devices need to be able to respond quickly. Like, the windows, doesn't matter if those are fast. The brakes need to be fast. The engine needs to be fast. So there's the processing power. And you also have to remember, in the case of automotive, a lot of OEMs are really are motivated by cost savings because they're making millions of these cars every year. And beefing up your microcontroller to be able to do fast encryption is not a inexpensive choice.
Yeah, so in one of the first things I heard of when I was talking to some of the Grimm team and understanding what the protections around this were supposed to be, it was more of the isolating certain subsystems from each other so that it was more difficult to send messages. In other words, your example before, which was the radio or the entertainment system, shouldn't be able to send messages that are associated with the brakes or even the doors.
Let me see if I can pull this up.
Oh, there we go.
So yeah, one way that you can kind of mitigate some of this risk is like wireless access for cars probably isn't going away. Like things like OnStar, they're convenient, they're a selling point for families. So it's not like we can just say, let's not do this as much as we might like to. One thing that you can do is have gateways in between different networks. So maybe instead of having everything on the shared network, there's actually, I didn't mention this earlier, but there's actually some gateways in here. So the parts of the car that are the most important, so the powertrain, everything that is going to be like a matter of life or death, goes on its own CAN network. And then the things that are less important might go on a second CAN network. And then the things that are, less important and also more open to risk, so anything that has some kind of wireless integration or ways that someone might attack the car, are going to be maybe on a third separate network. And if things on the different networks want to talk to each other, they can do so through a gateway, which is going to be kind of the go-between for the different networks, do some kind of filtering, and hopefully that kind of network segmentation will offer some protection to the more critical parts of the car.
So that kind of explains CANbus. We talked about some of the exchanges. Certainly, we couldn't drill. It's a whole nother class to drill specifically down into the different types of CANbus messages. But if you wanted to start getting into this, how would you prepare for that? As far as having the equipment, having the programs, and so forth that would interact with CANbus.
So I think the best way to learn this stuff is by buying a little bit of equipment and then plugging into a car and just kind of diving in. I think I'm a hands-on learner, so I think that's easier to learn and also way more entertaining than trying to go through it the kind of academic way. So you're going to need specialized hardware and then also software. So what we like to use at Grimm is a board from Machina. I think it runs about $90 or $100. This one plugs into the OBD2 port in your car. I have a smaller version of it, which is called the under the hood option. They both have a headers. Actually, this part I added on, but they both have headers such that you can connect this to the CANbus in your car, or a CANbus in your car, and then send and receive messages as though you were another device on the network. So this isn't the only option for hardware. There are other CAN transceivers and USB to CAN adapters with a CAN transceiver on it, for example, Cannable. This is just the one that we like to use. We also wrote a tool for intercepting, analyzing, kind of filtering through CAN messages that you're receiving. It's called CANcat. It's a Python-based tool. We have all the instructions here. It lets you record messages. You can bookmark things. So like the car unlocking example earlier, you can set a bookmark, which is like the start of it. It's always recording, but the bookmark kind of is a special marker. You unlock it, you stop with a second bookmark, and then you can filter in.
Okay.
You can use that to send messages. We use it for conferences. We use it for research that we do at our lab, and we're always adding things onto it. I'm actually working on upgrading this to Python 3 right now. We've got other kind of CAN adjacent protocols in here too. We've got J1939, there's CCP and XCP, which I'm working on, which is a kind of builds on CAN. There are other libraries out there. Scapy now has a CAN analysis in it. There is a Wireshark dissector for CAN. You have a bunch of free options.
Excellent.
There are plenty of paid options. So if you do this as a job, you might have your company buy something like Vector, Canalizer, or Canoe. This is really expensive, probably outside of the range of a hobbyist. So I'd stick with the free options. And then as a kind of high-level, all-in-one guide that will walk you through some of this stuff with your own car, I highly recommend No Starch Press for pretty much everything, but specific to this talk, I recommend the Car Hacker's Handbook.
Okay.
If you don't have your own car, or you don't want to experiment on your own car, you should also check out the Car Hacking Village. We'll be at DEF CON, but we'll also be at a couple other conferences. And what we've done for COVID, and we'll continue doing after the pandemic is over, is set up Raspberry Pis and other installations like these that are plugged into real cars or real test benches. You can SSH in to the Raspberry Pi or other device, and then you can interact with the car and then watch how it responds via webcam.
Oh, that's interesting.
Mm-hmm. We premiered that last year at DEF CON Safe Mode. It went pretty well for the most part. Not quite as fun as being in person, but it was still a cool idea.
Excellent. Jaime, thank you very much for coming here and talking to us. You've outlined CANbus and kind of just given us a brief overview of what it would take to understand it, to begin researching into it, and actually start interacting with it if you needed to do it for an assessment or needed to prepare for it. So I really appreciate the introduction that you gave there. Certainly, I hope that I'll get some experience, more experience on vehicles and also in robotics. That would be really interesting. I think this is something that is important for the industry, and we're going to find it in a lot of different processes. Is there anything that you would, anything that else that you'd like to, talk about, cover, any last minute thoughts?
I don't think so. I'd like to encourage people to just try it out. The Car Hacking Village option is a really low cost way of dipping your toes in, but there are ways to get into this, and you don't have to be a car person right away. You can, use this as an introduction to cars.
Well, once again, thank you very much for joining us today, and I appreciate your time.
Thank you.
Thank you for tuning in to another concept overview with the SANS ICS and Cutaway Security teams. Please let us know if there are other topics you would like us to cover in the comments below. If you enjoyed the content, please be sure to like and subscribe to the SANS ICS YouTube channel. This has been Don C. Weber of Cutaway Security. Go forth and do good things.